Prepared introduction. Hello, I'm Daeon Lee. As introduced, I am a professor in the Department of Aerospace Engineering at KAIST. So my talk is about the soft robotics and the space explorations. More specifically, I am working on origami stuff. So I think that most of you know the origami, right? That's skateboarding is a kind of a hobby stuff when you're a child. But we can't connect them. So my journey is that how can we create some kind of innovations in the space robot stuff in using the origami? So let me introduce you. So because of the time that I practically did it, so actually I bring some demo stuff or something, but I think that we don't have enough time. So maybe after end of these sessions, then maybe you can have some opportunity to do that. Okay, so first I try to explain what origami is. Of course, everyone knows what origami, but let's think about that. Okay, so this is one of the masterpiece of the origami, and the amazing thing here is that we can create this kind of complicated shape using just a single piece of paper. They never use a cut, they never use a glue. They just holding a pure paper to create that. And this is more amazing stuff. So can you see all the details here? All the scales and the counts and the map details. So same rules apply here. They just use a single piece of paper, the rectangular paper like that. So origami is not just a hobby. It's a really sophisticated mathematical work that how we can connect between the two distinctive shapes, such as this plain paper to some arbitrary shapes. So this is some the pathway we say that about the connecting the different shapes. But if we expanded that their definitions, that we can do more. So this is one of my famous favorite things that I think that most of you also like that, right? The chicken box. Think about that. So we usually care about the chicken, but we never thought about this as a box. But let's think about that. So if you put some your precious stuff in the box and just packing up, then it can be quite rigid, right? So you can stack up the multiple things on it, or if you do not need that, you can just disassemble that, dispose it. It's lightweight, efficient, and effective solutions. So in origami engineering, we can say that this origami is a kind of the mechanical design tools that we can create the really complicated motions using simple manners. So my first work is using this kind of concept to create the transformer wheel project. So of course I've done a lot of projects, but because of the time limit, I just introduced this project. So the purpose of this project is applying this kind of origami-inspired technique to transform wheels. Then maybe the first question is that why do we need a shape-changing wheel? So this is quite trivial things. So if we have some larger wheels, we can curve the larger steps, and if we have small wheels, then we can curve the small gaps. If we can switch the wheel shapes, then we can create a better robots that can overcome the various struggles. Then why we should use origami? So as I explained before, origami can offer some great solutions, such as the live shape changing and also easy verification. So think about that. This is all the connected structure. But if we want to create this kind of motions using linked systems, then maybe this is quite challenging, right? You have to think about how they connect them, how they fabricate them. But using the origami, just folding a paper, then we can solve it. So then the next question is that how exactly we can create some functioning machines using origami. So this kind of design step is maybe you're not familiar with, but so actually this is quite familiar with the common machine design concept. So think about that. If we want to create something, what's the things that you have to think of first? First thing is that we have to find the building blocks that can create the world. So origami is the same. I have to find some building blocks, and in origami world, that there are a lot of building blocks already exist. And among them, I find that the work pattern is the most promising pattern because it has some circular shapes and it expands. So I use this pattern and define that as 3 by 8. So I made some final shape. So we need the rims, the main of the wheel body, and also we need some support. So these are support structures. So this is my final design. So I'm quite happy about that, but the problem is the interface. So I think this is always a problem with most of the mechanical design stuff. So This is the wheel structures. That means that I designed the wheel body, but I have to connect this wheel body to wheel shaft. And I need a really reliable connection with that. But the issue here is that it has some arbitrary shape. And the more challenging thing is that when you change the wheel shapes, and this boundary is also changing. Then how we can solve that then? So after a few months of their iterations and their think about that, I find that I designed this kind of shapes, and I made that the boundary condition for it to be the same even after you change the shape. So of course this is a simple pattern, but it's really critical for our project. So after that, I designed the whole wheel structures and do some calculations as always the engineer do. And I finally designed this wheel system. So as I mentioned before, if it can change the wheel size, then it can overcome the high steps by expanding its wheel size. And when we're at the small gaps, then we can shrink them. So it's quite a successful demonstration of that. But this is a wheel, right? Then ultimate application of the wheel may be applying that concept to real scale figures. Of course, the first time, I think that this is totally impossible, this is totally nonsense. But I think the speed of the researcher is just challenging to something like impossible. So at the time, my professor really encouraged me to do that. So actually at that time, I don't want that, but my professor encouraged me. So this is sorry. So this is a transforming tire project and targeting the applying to the actual scale figures, and then the target payload is around the 1,000 kilograms. Of course, there are a long story that I need the whole day to explain that, but here I just jump to the conclusions. So after testing a lot of patterns, and something is the stiff, something is the very accurate, and many of the trials, and I finalized this pattern. And this is some of the demonstrations. Okay. And after this is 2 years of the iterations, and after that, I tested the wheel to some just configure. So at the time, the vehicle of course doesn't have some function of the wheel transformation, but we just want to test that this is really feasible or not. And after confirming this success, then we actually designed some special vehicles that can transform this wheel. So this is, I think that this is kind of some breakthrough in origami engineering. So previously, when you think about origami engineering, we just think about the small toy-like stuff. But here, we prove that we can apply that origami concept to more extreme conditions. And when I present this kind of stuff, then there's always questions there. What about just making this kind of structure using the linkages and there's some kind of kinetic structure, link and the varying of some things? But my answer is that if you create this kind of the complicated soft-scale kinematic structure using linkage systems, if there's some impact is applied here, that distort or they make some bend or has some issue in some part, and it ruins everything. So this is only possible because all of the structure is made by soft material. Because it is a soft, so it can absorb all the impact, not only the impact, and also it can, so even if there is some dispersion, it can absorb that. So this is something like an actual tire, because all the linkage is made by some membranes that are used for tire. But it can still quite as functional and can endure a lot of the tough environments. So this is a story. And let's shift our gear to the space stuff. So anyway, this kind of space engineering is always actually this very well-established field of the origami, because space is also has some issue of the space, right? There's we don't have much space in it. So this kind of floating technique is quite a useful tool for us to solve the space issues. But previously we developed a lot of the mechanisms, but I think we need more, because everyone here, I guess, knows that we will soon establish some coordinates on the lunar surface, right? That means that so previously we just beach there, right? But now we have to live there. That means that we need a building, we need a car, we need the farms, many things. So ultimately, we need everything on Earth to bring to the moons. That means that I think that we have to hold everything on Earth, almost everything, Of course, someone trying to just 3D print it, but I think that these two solutions should be combined together. Anyways, then what needs for that? So of course, in origami, the theory, we can form everything. But the problem is that we have to think about the mechanical properties and how to actuate them, and also how to fabricate them, what kind of material we can use. So there are a lot of questions to make. So my work is that combining all these questions together and then design some new kind of mechanisms based on that. So also there are a lot of projects, but because of limited time, I only introduced the two signature projects. First thing is the ground mobility systems. So AK is a rover project. So as you know that these days Luna is quite busy place. So I mean the many country, not only for national institute and also for the private company is coming to Luna. And Korea is also preparing some Luna landing missions. So shortly we are going there 2030 and also we will send the lander until 2032. Then where should we go? Of course, there's a lot of the remaining distribution discussions there, but maybe each solution is that with some plan and the plan and each plane surface. But actually, Luna has a more interesting locations such as the crater or permanent shadow regions or something like a rubber tube. But the problem is that here, the center. So of course there are a lot of issues, but this is the most critical problem as a mobility of the lunar systems. Because think about that. Think about that. When the rover loses their mobility, then it loses their everything. So this kind of the express mission can be stopped because of just the center trap. So to avoid that, all the rover pilot should be very careful. So they limit the rover speed as less than the 5 centimeters per second. And also if they go to some steps, then they stop and scan all the area and find the safest path for there. If we can use a really big fields, then everything can be solved. So we don't have to worry about that kind of center trap or something. But the problem again is that the space of the space. So I am a diploma wheel designer, so I'm quite confident about that. So I'm trying to do that. But actually, that is not the easy task. So here's some challenges. So first thing is that we have some serious limitation in the mass and the volumes. This is not only the scale things. We just need some small. So this wheel should be. The mass and the volume of wheel should be comparable with just the normal wheels. So deformer wheel and the normal wheel should have same mass. So that's the really critical constraint. And also, we can use our actuator sensors because of the reliability. If it has some issue in the sensors or actuators, then yeah, it has going to the value. So we have to avoid it. And also, we have to think about the extreme environment. So it seriously limits the material we can use. And also, our system should have an impact resistance. That means that some kind of crack or crush of the wheel can ruin everything. So we have to avoid it. So most importantly, we have to secure the operational reliability, right? So it shouldn't ever fail. So in any case of the failure, then it ruins our whole mission. So we have to avoid that. So designing the deformed wheel that satisfies all these conditions, that's not the easy problem. And I think that's why there's no presented the actual case. We can actually apply the deformed wheel concept to the Luna rover. So this is just a promising concept, but because of these challenges, this is hard. So our team has total different approaches. So this is the result. We developed this system with the UEM, which is a startup company targeted for Luna rover. And you can see that this is the wheel structure, but it can deform. And because of the simplicity of the structures, then it can endure high impact. Because this is just nothing, just a steel string, the spring steels. And also, because it is simply made by spring steels, then we don't have to worry about this kind of extreme conditions. Because we don't have to worry about the hinges and joints and the bearing stuff. And also, we tested the mobility, the rover, under the rubber tubes. There's kind of some extreme environments here. So actually, this is kind of the huge achievement of our teams, and the project is reported in the main page of the science web pages, and also we have some lot of videos. And I think the lesson here is that everyone think about this redox system. They just think about the rigid part, rigid stuff, and the heavy stuff. But using that kind of the soft material, we still can have a chance to create a more reliable and robust system. So because of time, I just quickly introduce the other project. So this is the active debris removal project. That means that this is in more easier. This is the satellite designed for clean up the space. So this is funded by CASA and developed by the SATRAC, the KAIST. So our job is that provide some special gripper for satellites. So I think that most of us are familiar with the space trash problem, so I'll just skip this part. And the Korea, the KAIST also planning to design the satellite to prevent the emissions. I just skip part. And think about that. What's the challenges in this space gripper design? So this is the common gripper. When you think about that, when you design the gripper, it should have some fingers and also it should have motor, right? What problem is that we need a lot of motor. So this is the key difference between the just common satellite and this kind of specially designed satellites. We need a lot of actuator. That means that we require a lot of, not just the actuators, we also need sensors, drivers, and this means that we have a lot of failure points. So imagine that if you have a single of this motor is failed, then it's hard to grasp this object. So here we also use a totally different approaches. So this is some special gripper we propose. So it's made by the single-to-three. I think that so we usually create some kind of flower using this kind of paper, isn't it? But if we slightly change our mind, then we can use that paper. The good thing about this paper is that it just needs a single actuator and it doesn't need any sensors, but we can grasp various objects in easier way. That's an easy task for us. And also we tried that just for fun, and it's quite successful. And we done that. How small object can grasp, and we also success here. And good thing about this gripper is it's really tough. So this is me, and we proved that this gripper even can hold the humans. This is the pedals around the 100 kilograms. So I have some demo here. So if you're interested, then please come later. Maybe I can give you some chance to demonstrate that. Okay. So this part, and this is the simulations that how we actually do the missions. So of course this is not the final version. This is the dummy version. But the important thing is that in space, one of the challenging parts is that to detect the object's exact positions. But because of this soft gripper, even with there's some errors, we still can. It is able to capture the object. So this is the end of my presentation. Just show that. This is the beginning of everything. So when I was a master student, the program manager from AFOSR, Dr. David Stugger, come visit our office and show us this video and talk to us that this is what we're doing about. This is the future we want to be. And he also say that, of course, this is quite challenging and maybe it's impossible, but still we know that this